Thank you for tuning in to this talk. Today I will be talking about the Strongish planted clique hypothesis and its consequences. And this is joint work with Aviad Rubinstein and Tselil Schramm. Both of them are from Stanford University. So in the planted clique problem, we consider the following two distributions. The first one is the distribution Gn², which is simply the uniform distribution over all graphs with n vertices. Equivalently, you can think of this distribution as each edge in the graph being present with probability 1/2 independently. Another distribution that we consider is the planted distribution. In this distribution, the graph is first generated the same as before using Gn², but then we add to it a random kappa size clique. For example, maybe this is the graph we generate from Gn². If kappa is 3, we would pick 3 random vertices, so maybe these are the 3 vertices. So we add the edge between them so that they become a kappa clique. In the planted clique problem, we are presented with a graph G, which comes from either Gn² or the planted distribution. And our goal is to distinguish between the two. Specifically, if G comes from the former distribution, we want to output random with probability say at least 2/3, and if it comes from the planted distribution, we want to output planted with probability at least 2/3. Several algorithms are known for the planted clique problem. The simplest algorithm exploits the fact that in Gn², the size of the largest clique concentrates around 2 times log n. This means that we can try to enumerate to try and find a clique of size significantly larger than 2 times log n. If we find one, then we know that G likely comes from the planted distribution. So this gives us an algorithm that runs in n to the order of log n time, and this works for any value of kappa. Furthermore, when kappa is too large, specifically if kappa is at least the order of square root n, it's also known that the problem can be solved in polynomial time. However, below this threshold of square root n, it is not known whether the problem is solvable in polynomial time. And many researchers in fact believe that when k is little of square root n, planted clique cannot be solved in polynomial time. And this is formalized in the so-called planted clique hypothesis. So in recent years, the planted clique hypothesis has been used as a basis to prove many hardness results, including an inapproximability result for densest k subgraph. So recall here that in the densest k subgraph problem, we are given a graph and an integer k, and we would like to find a subgraph of size k that contains as many edges as possible. It has also been used to prove hardness for the base Nash equilibrium, and also for some more average case problems such as sparse PCA, and many more. So in this work, we are proposing a variant of the planted clique hypothesis, which postulates the following. For kappa that is a sufficiently small polynomial in n, so here throughout this talk I will just write n to the 0.1 here, but you can replace 0.1 by any sufficiently small constant. Then the planted clique problem cannot be solved even in n to the little of log n time. In other words, we are saying that for this range of kappa, there is no algorithm that achieves significant speed up compared to the brute force algorithm that we discussed earlier. We call this hypothesis the Strongish planted clique hypothesis. And for those of you who are familiar with the exponential time hypothesis and the strong exponential time hypothesis, here the reason that we don't call it the strong planted clique hypothesis is that in the strong ETH, we would also specify the constant in the exponent, whereas here we're not specifying the constant, so this is more akin to the exponential time hypothesis compared to the strong exponential time hypothesis. So having stated the hypothesis, let me note that there are a few evidences in the form of lower bounds that can be viewed as supporting the hypothesis. In particular, Barak et al. Showed that if you take the natural sum of square relaxation for the planted clique problem, then it cannot be used to refute the Strongish planted clique hypothesis. Similar lower bounds are also known for statistical query algorithms. Since sum of square and statistical queries are a large family of algorithms that encompass many of the known techniques, this suggests that refuting the Strongish planted clique hypothesis is hard and is possibly out of reach of the currently known techniques. Okay, so hopefully I have convinced you that this hypothesis is at least plausible. Let us now move on to discuss what we can actually prove using this hypothesis. So the result that we can achieve assuming the Strongish planted clique hypothesis can be divided into two groups. First is tight hardness of approximation results, and second is tight running time lower bounds. The main result in the former is for the densest K subgraph problem, where we show that there is no polynomial time little of K approximation algorithm for the problem. And note that the approximation ratio little of K that we can prove here is tight because there is a simple algorithm that can achieve K approximation for the problem in linear time, where you just pick a vertex with highest degree and pick as many of its neighbors as you can. Now, using this result and known reductions in literature, we get tight hardness of approximation results for many problems, including the smallest K-edge subgraph problem, the Steiner K-forest problem, and the directed Steiner network problem, all of which we get little of square root K hardness of approximation ratio. And also for the densest K subhypergraph problem, where we prove 2 to the little of K hardness of approximation. I will not go into details of previous work on each of these problems here, since each of them has a pretty long history. But if you're interested in learning more, please check out the full version of the paper where we have summarized the previous works on each of the problems. On the tight running time lower bound front, our main result is that there is no n to the little of K time algorithm that can achieve constant approximation ratio for the densest K subgraph problem. And notice here that the running time lower bound is tight because there is a trivial n to the order of K time algorithm for densest K subgraph that just enumerates to all the possible subsets of vertices of size K. So using this result, we can prove tight running time lower bound for graph pattern detection problems. So in this problem, we are given a graph pattern, which is just a graph of size K, and we are given a host graph, which is a much larger graph of size N. And the goal is to find whether the host graph contains the pattern. There are two versions of this problem. The first one is when the pattern has to be an induced subgraph in the host graph. And the second version is when the pattern can be any subgraph and not necessarily induced subgraph of the host graph. So in the first version, the induced version, we can show n to the little o of K time lower bound for any K vertex pattern. On the other hand, for the not necessarily induced pattern, we can show that this running time lower bound holds for most K vertex patterns. I would like to quickly note here that all of our lower bounds also hold for FPT algorithms. So this means that even if we allow the running time of the algorithms to depend as any function of K, such as exponential in K or doubly exponential in K even, our results still hold there. Since all the lower bounds that we discuss here follow from reductions of the two top lower bounds. We'll be focusing only on those two for the rest of this talk. And moreover, in fact, these top two lower bounds are proved using the exact same reduction and the exact same proof, just with slightly different choices of parameter. Okay, so now let us discuss about this common reduction between these two hardness results. So here I just copy the two hardness results from the previous slide for convenience. In our reduction, we will start from the planted clique problem. So in the yes case, our graph G will be sampled from the planted distribution, where here our kappa is n to the 0.1. And in the no case, G will be sampled from the random Gn½ distribution. Our reduction has three parameters, K, L, and N. And it will produce a graph G prime with the following properties. In the yes case, G prime will, with large probability, say 0.9, contains a K clique. Whereas in the no case, again with large probability, any K vertex subset of G prime will have a small number of edges. Specifically, the bound we will get is order of K times log n over L. And the size of the graph, or the number of vertices of the graph G prime, will be big N, which in our reduction we will always choose to be n to the order of L. Now recall that the Strongish planted clique hypothesis give a running time lower bound of n to the omega of log n of the starting planted clique problem. And since the size of the new problem, big N, is just the original n to the order of L, we now get a running time lower bound of big N to the omega of log n over L. And for the inapproximability ratio, notice that in the yes case, there is a solution which is the K clique that has order of K square edges, whereas in the no case, we have an upper bound of K times log n over L edges on any solution. So we get an inapproximability ratio of K times L divided by log n. So once we have this reduction, it's pretty simple to derive our two main hardness results. Specifically, for the first one, we may pick L to be little o of log n. Here we get inapproximability ratio of little o of K and a running time lower bound of n to the omega of 1. This means that no polynomial time algorithm achieves approximation ratio of little o of K for densest K subgraph. For the latter, we can pick L to be some constant times log n over K. So this will give us constant inapproximability ratio and running time lower bound of n to the omega of K. So in other words, there is no n to the little o of K times algorithm that achieve constant approximation ratio for densest K subgraph. Okay, so with that in mind, we only have to describe this reduction and prove its property. So this reduction is the so-called randomized graph products, which has been used since at least the late 80s by Berman and Schnitzger. And the reduction works as follows. So recall that we start with a graph G, and we have parameters K, L, and N. What we will do is, first, we will pick n random subsets of vertices of G, S1 to Sn, each having L vertices. And then we will construct one vertex in G prime for each of this subset. And we add an edge between two subsets, Si and Sj, even only if their union induce a clique in the original graph G. For example, here is a possible construction. If our L is equals to 2, we will pick S1 to Sn to be random subset of size 2 from the vertices of the original graph G. So maybe we pick S1 to be V2, V3, S2 to be V1, V2, and S3 to be V3, V5. So we will then go and create one vertex for each subset in G prime. And then for each pair, we will consider their union and see whether it's a clique in G. For example, in S1 and S2, the union is V1, V2, and V3. which is not a clique in the original graph G, because V1 and V2 doesn't have an edge there, so we do not add this edge. On the other hand, S1 and S3, their union is V2, V3, V5, which induce a clique in the original graph G, so we add an edge there. And we continue this process until we finish the construction of the entire graph G prime. Okay, so that's it. That's the entire reduction. And note here that the number of vertices in G prime is exactly n, as we claimed earlier. So before I go forward, let me note here that this is not an original reduction by any means at all. As I stated earlier, it has been used in hardness of approximation before by Berman and Schnitzker, who use it to prove hardness of approximation for the clique problem, and it has been continued to use until very recent work, both for clique and for densest K subgraph. Another point I would like to note is that in an earlier work of Alon et al., who used the planted clique hypothesis, not the Strongish planted clique hypothesis, but the original planted clique hypothesis, to prove hardness of densest K subgraph, they also use a similar reduction with just one difference, which is that their subset SIs are taken to be all subsets of size L, whereas for us here we are picking only some random subsets. And since Alon et al. Was looking for hardness in terms of the graph size n, their results are incomparable to us. So now let's prove the desired properties of our reduction, starting with the yes case. So here recall that we have that G is drawn from the planted distribution, where the clique size kappa is n to the 0.1, and we want to show that with probability 0.9, G prime doesn't contain a K clique. So here we will pick the big N to be 10K times n to the 0.9 times L. And note here that this is still n to the order of L, because here our K will be very small. And the proof of the completeness is as follows. Let's C be the clique in G of size n to the 0.1. Notice that ignoring lower order term for the moment, each set Si is a subset of C with probability roughly n to the minus 0.9 times L. This is because each vertex in Si belongs to C with probability n to the minus 0.9. So this means that in expectation, there will be 10K of the subset Si that are subsets of C, the clique in the original graph G. And we can turn this to into a probabilistic statement that with probability 0.9, at least K of the subset Si's are subset of the clique C in the original graph. Now, recall from our definition that when Si union Sj induce a clique in G, we add an edge between them. Since these KSIs are subset of C, the union of each pair of them induce a clique in G. As a result, these SIs will form a K clique in the new graph G prime. And that's it. That's the entire completeness proof. Let us now move on to the soundness proof. Recall again that in the soundness case or the no case, we have that our graph G is drawn from the Gn.5, the random distribution. And we would like to show that any K vertex subgraph of G prime contains at most K times log n over L edges with probability 0.9. Now, the overall idea in showing this is pretty simple. So we'll consider each subgraph that exceeds this bound, in other words is too dense in G prime, and bound the probability that it exists in G prime. And then we'll just take the union bound over these too dense subgraphs. So let us start with the former. How do we bound the probability that each too dense subgraph exists? So let's consider any possible K vertex subgraph of G prime with at least D times K edges, where D is a parameter we will choose later. Notice here that each edge in G prime corresponds to a clique in G, which is a union between the two subsets Si and Sj. Now, since each of Si and Sj has size L, this corresponds to roughly L square edges in the original graph G. Now, since the subgraph that we are considering contains D times K edges and each edge in G prime corresponds to roughly L square edges in G, this means that the entire subgraph will correspond to roughly D times K times L square edges in the original graph G. Now, this statement that I just said actually doesn't follow as trivially as I might have led you to believe. And the reason is that each edge in G might appear in more than one pair of subsets Si, Sj, so it might have been counted multiple times in our argument here. However, it turned out to not be that big of a problem because our set Si's are random, and we can show that for these random subsets, the number of repetitions that we are counting is not too much, and in fact, the subgraph still corresponds to omega D times K times L square edges in the original graph G. Now, finally, recall that the graph G is just drawn from Gn², so each edge appears independently with probability 1/2. So the probability of this subgraph appearing in G prime is only exponentially small in D times K times L square. Alright, now we can move to the second step. And in the second step, notice here that the number of the two dense subgraphs is dominated by the number of choices for its vertices. And there are K vertices, so there are roughly big N to the order of K such subgraphs, and this just equals to little n to the order of K times L. So here we can use the union bound, and we can get that the probability that G prime contains at least one of such two dense subgraphs is n to the order of K times L times exponential in minus D times K times L square. So now if we pick D to be a sufficiently large constant times log n divided by L, then we will have that this number is at most 0.1. In other words, with probability 0.9, we have that any K vertex subgraph of G prime contains at most order of K times log n over L edges. And that concludes our soundness proof. So modulo some simple calculations. Those are basically all the technical components of our work. So let me conclude here. We propose a variant of the planted clique hypothesis, which we call the Strongish planted clique hypothesis, and prove several tight inapproximability results and tight running time lower bounds using the new hypothesis. There are quite a few research directions that might be interesting to pursue here. First is, can we get a tight inapproximability ratios also in terms of n? Note here that in our work here, we get tight inapproximability results, but only in terms of k. It would be interesting to strengthen this and get tight inapproximability in terms of n as well. Another kind of more open direction is to find more applications for the Strongish planted clique hypothesis, and this also include applications that are beyond hardness or approximation result. And finally, it would also be interesting to prove our hardness results, but under different assumptions, such as hardness of random CSP, for example. And that's it. Thank you all very much for your attention.